a random variable is completely defined by its cumulative distribution function, which we abbreviate as the CDF. We denote the cumulative distribution function as f sub x of script x. Here x, the big capital X, refers to the name of the random variable, and this script x is just a variable. And the CDF is simply the probability of outcomes such that x of w is less than or equal to x under the random variable mapping x of w. Often, we abbreviate this as the probability that x is less than or equal to x. Okay? And we understand that x equals to x simply refers to this event of picking an outcome w which maps to a value less than script x under the probability, under the random variable mapping x. Okay, so let's see some, so by the way, notice that this is a Borel set of real numbers. Hence, automatically this event is going to be measurable by definition of a random variable. So let's see some examples. Let's see the simplest binary random variable. We last time defined an indicator function, which was also a binary random variable. We'll call this a Bernoulli random variable with parameter p. The Bernoulli random variable with parameter p takes two values, 0 and 1. So x is Bernoulli with p if x is equal to 1 with probability p 0 otherwise. So this is exactly the same as the indicator function. You know, with probability p it is 1, with probability 0. With probability 1 minus p it is 0. It could it could refer to the success or failure in an experiment. I toss a coin, suppose I want to get heads. If I get heads, I record a success. In other words, x is 1. If not, I record a failure. Let's see. You know, I could go back and think of a sample space where there's a success or a failure, and those are the only two possible outcomes. And the probability of success is p. Suppose p is less than 1 minus p. Oh, sorry. Success maps to 1, and failure maps to 0. And the probability that I get a success is p. Okay, so now what is the CDF of this simple random variable? CDF is nothing but the probability that x is less than or equal to x. So it is 0 if, clearly, if x is less than 0, because x does not take any values before 0. And it is the probability that x is equal to 0, okay, which is 1 minus p, if script x is between 0 and 1, and the probability that it's less than or equal to x is less than or equal to script x is 1 if script x is less than or equal to larger or equal to 1. Okay, so this gives us a staircase type function when we plot the CDF as a function of script x. So suppose p is small, suppose p is 0.2, okay? So this is 0.8, this is 1, and this is 1. The function starts at 0, it jumps to 0.8 at 1, and it jumps to 1 after 1. It jumps to 0.8 at 0, 0.8 at 0, it jumps to 1 at 1. Now how about these jumps? Actually, if you look, 0 is inclusive here, so the jump is closed at this end, and this is open. Okay, so this is a discontinuity where the function f(x) of x is continuous from the right. A CDF will always be continuous from the right. Okay, again here at this jump, the continuity is from the right, and this point is open and that point is closed. So that's how it is. Right. So notice that the CDF function is non-decreasing. Sometimes it is constant, sometimes it's flat, but it does not decrease. This is not a coincidence. CDFs will always be non-decreasing, which we can easily show it. But CDFs do not need to always look like a staircase function like this. They can have continuous parts together with jumps. They can, but they will be non-decreasing. So with that, in fact, let's talk a little bit about the properties of a CDF. Okay. First of all, why is f(x) of x is why is f(x) non-decreasing? The explanation is very simple. It's a probability, and if a is less than b, the probability that x is less than or equal to b can always be decomposed into, by the additivity of probability, probability that x is less than or equal to a plus the probability that x is between a and b. Okay, but since this is greater or equal to 0, we obtain that probability x is less than or equal to b is always bigger than or equal to probability x is less than or equal to a. Now, equality happens if this, the probability that x is between a and b is 0. Okay, so what else? The limit as x goes to infinity f of x is 1 because this is simply the probability that x is less than infinity. Similarly, the limit as x goes to negative infinity of fx is 0. As you can see, they always start at 0. And this is because this is the probability that x is less than negative infinity, and that should be, the probability should be 0 because x is a real number. It is always, it cannot be less than negative infinity, obviously. Okay. As we just discussed, as a third property, we can write that fx is continuous from the right. It is always continuous from the right. What does that mean? The limit as h goes to 0 of f x minus h is equal to x plus h, right, is equal to fx of x. This is always true. You can easily show that. Note that if I'm approaching a point, x from the left. Okay, so suppose this is this is the CDF. If I'm approaching the point x from the left such that I'm taking the limit as h goes to infinity, h goes to 0, f x minus h, all right? I could always also write this as f x minus, just before the point x, okay? This is nothing but the probability that x is less than x. X is less, strictly less than x, okay? And it is not necessarily equal to the probability that x is less than or equal to x. When is this not equal? It is not equal when there is a finite probability that x is equal to x. When the random variable takes on a given value with a non-zero probability, we say that the distribution has an atom at that point, and there is a jump in the CDF equal to the probability that the random variable takes that value. Okay, so that causes discontinuity from the left. All right, so now similarly we can write that the probability that x is between a and b, where b is included, a is not included, can be written as fx of b minus fx of a. All right, and because of this, as a consequence, probability x equals a is fx of a minus fx of a minus. So these things, as I said, are non-equal when there is a positive probability, and that constitutes a jump at a. Okay, finally, there's a theorem which says that if you find a function f that satisfies properties 1 through 3 here, then you can find some probability space omega fp and define a random variable such that f is the CDF of this random variable. So a CDF completely defines a random variable. Once we are given the CDF, we know everything there is to know about the random variable, and in fact we do not need to go back to the sample space description at all. We do not need, once we have the CDF, we can compute everything about this random variable without going back to the sample space description.